Hey y'all, I just wanted to go ahead and go over the review with you. I'm going to work out every single problem, and that way, if you're looking at the key and just kind of confused about what's going on there, hopefully these explanations will help you understand and get you ready for the test, which will be next class. So let's just jump right into it. Let's start with number one. Which says we want to solve the equation 3/4 times x is greater than -9. And we'll also graph this on a number line, or graph the solution set on a number line. So right away, we've got some number times x is greater than some other number. And to solve these, you're going to take essentially the exact same steps that you would if it were an equation, the same order of steps in terms of like if you have to use distributive property, followed by combining like terms, followed by moving the constants, and then finally dividing by the coefficients. You're going to take those exact same steps in the same order. There's really only one difference between solving an inequality and solving an equation, and that is if you happen to run across a problem where you have to multiply or divide both sides by a negative, then you would flip this sign. Now that doesn't happen in this particular problem, but as we go through these, we're going to be checking to make sure that we don't miss that step. So here we have 3/4 times x. So what we want to do is we want to divide both sides by 3/4. Now I know working with fractions can always be a little tricky. So use your calculator. I mean, you've got it there. There's no reason not to use it. You got to use your resources wisely here. I'm not going to bother trying to divide fractions in my head or even on paper. I'm going to go ahead and do -9 divided by 3/4 and get my number that way. So I do get -12. So my final answer here would be x is greater than -12. Okay, so that's my solution set written as a statement, as an algebraic sentence. But I also want to express the solution set graphically. And so the way I do that is I'm going to draw a number line. I'm going to label 0. Typically, the way I like to do this is use 0 as a reference point so I can clearly distinguish between the negative values and the positive values, and then throw on the number that is in question here, which is -12. Now, before I actually do the number line here, I'm going to just throw a couple of notes up here that I'll keep referring back to. Okay, there's 4 different inequality symbols that you're going to run into: less than or equal to, greater than, or greater than or equal to. And what you want to know is, as long as x is on the left-hand side, so I'll just throw an x on the left-hand side of all these, question mark, question mark, question mark, question mark. You want to know what each of these graphs look like. So if it's greater than, then the arrow will be pointing to the right, okay? And if it's less than, the arrow will be pointing to the left. If it's equal to, you're going to draw a closed circle. So like this would be a closed circle. This would be a closed circle. These would be open circles. And what you're saying is that particular number where you're drawing the circle either is or it isn't a solution to the inequality. So, right, if you got x is greater than the number, your arrow should be going to the right. If it's less than the number, it should be going to the left. So this is how you're going to decide what kind of point to draw in, whether it's open or closed, but also determine which way the arrow should be pointing. So if x is greater than -12, because it's strictly greater than, it doesn't include -12, we're going to do an open circle. And then because the solutions exist where x is bigger than -12, we're going to point the arrow in the direction of where the solutions are. So all these numbers are bigger than 12. Let's look at number 2. We have -3.55g is less than or equal to -28.4. This problem is set up very similarly. Okay, we've got some number times the variable. And so to undo that multiplication, we're going to do the exact same thing as number 1, and that is to divide both sides by that coefficient. When we go ahead and divide both sides by that -3.55, we need to be aware that we are dividing by a negative. Okay, so this is going to be a case where we need to flip the sign of the inequality. In other words, change this less than to greater than. Let me move this up a little bit for you. So These will reduce to 1, and so we get G is greater than or equal to, because remember, we're flipping the sign due to the fact that we're dividing by a negative. And again, I'm not trying to do all that division in my head. No way, no how. There's no reason to try to open yourself up for mistakes by doing that. So I'm going to divide this using my trusty calculator. Do the hard work for me. And look at that. Oh, that works out nicely. I like that. Okay, so we get an integer there, 8. And so my solution here would be G is greater than or equal to 8. When I go to graph this on a number line, just like every graph, I'm going to include 0. And I'm going to include the number in question here, 8. And then there's 2 questions I need to ask myself before I throw anything down. And that is, should be an open or closed circle. And because 8 is a solution to the set, because 8 does equal 8, we're going to do a closed circle. And if G is could be greater than 8, that means all the values, all the numbers that are bigger than 8 will be included in the solution set. So we're going to draw the arrow going to the right. All right, let's take a look at number 3. Now we're getting into some word problems here. It says Mariana receives a $20 gift card for downloading music and wants to determine how many songs she can purchase. Each downloaded song costs $1.29. If M represents the number of songs downloaded, which inequality represents the given situation? So in this case, we're not actually asked to solve anything. We're just asked to take what is written in English and translate it into an algebraic statement. In this case, an inequality. So if each song costs $1.29, we're going to say that $1.29 times the number of songs, this expression will represent the total amount of money she's spending, right? Because she's got to spend $1.29 for each song. And if you only have $20, that means that you can't spend more than $20. The amount that you spend has to be less than or equal to $20. And so this would be your inequality. It's not solved. It doesn't ask you to solve it. But if you were to solve it, you would divide both sides by 1.29, and you would go from there. Number 4 is another problem where we're just trying to set up the inequality. Your brother has $2,000 saved for a vacation. His airplane ticket is $637. Write and solve an inequality to find how much he can spend for everything else. So you got that $2,000 that he can spend. All right, that's going to be the maximum he can spend. So we can expect this piece of our inequality to be kind of similar. So we're going to write an expression first for how much he's actually spending, just like here, and then set that less than or equal to the 2,000. So if he only has to buy one airplane ticket, and let's assume that that's a round trip ticket. It doesn't really say, so there's a little bit of ambiguity in this problem, but let's assume that he only has to buy a single airplane ticket, and that'll get him where he's going and get him back. So we have 637, that's his airplane costs, might be a better way to word that, plus anything else he wants to buy has to be less than or equal to 2,000. So that would be the setup there. If you were to solve this, you would subtract 637 from both sides. All right, that's section 1. Let's move on to section 2. Now, section 2 is a little bit heavier on the solving aspect, so we'll just go through these and graph their solutions. 4x plus 6 is less than or equal to 18. Again, so what we've got here is a 2-step equation, and you would solve, or inequality rather, you would solve it exactly the same way as you would as if this was an equal sign. So you're still going to subtract 6 from both sides and then divide by 4. The only thing you have to look out for with these inequalities is that if at the end you divide or multiply both sides by a negative, then you got to flip the sign. This ain't going to happen on this one, but it will happen here and there. So we just want to be on the lookout for that. The first step here would be to subtract 6 from both sides. When we do that, we get 4x is less than or equal to 12. Then we want to divide both sides by 4. And so we get x is less than or equal to 3. So that would be our solution set. The way that would look on a graph is I'm going to put 0 as my reference, 3, as the number in question. And because it could be equal to 3, I'm going to do a closed circle, and the arrow is going to the left. Here's a little pro tip to kind of remember the arrow thing. As long as your x is on the left-hand side, so I'm just going to give 2 quick examples here. As long as the x is on the left-hand side like this symbol actually gives you an indication of which way the arrow should go, right? This way, that way. So you just want, you want to be careful there because the x does have to be on the left-hand side for this little trick to work. But if it is, then this can be a quick way to just kind of see that, oh, it's pointing this way, so I know that it's got to point this way. It is important to really understand why it's pointing that direction. It has to do with the fact that these solutions are less than 3. But if you just want a quick way to remember how to do that, that might help you. Let's do number 6. I've got 12 is greater than 2x minus 8. So the first step I'm going to do here is add 8 to both sides. That'll give me 20 is greater than 2x. Something you might notice about this problem is our x is kind of stuck over here on the right side. It's not a big problem, but it is something that we probably want to take care of. And by that, I mean we want to eventually write this so that x is on the left side. It's not wrong to write it like this. Like there's nothing logically incorrect about this statement. But typically, when you write these inequalities, it is advantageous to you to write the variable on the left-hand side, especially if you want to take advantage of this little trick that, this little arrow trick that I was talking about earlier. So that won't work if it's on the right side like this. So I'm going to go ahead and rewrite this. And the way you do that is just to flip the entire thing. So like I would rewrite this as x is less than 10, because if 10 is bigger than x, that means that x has got to be smaller than 10. So here's my answer. Again, this is not a wrong answer, but like if in a multiple choice setting, it's not likely that the answer is going to be written like this. So you want to be able to make that switch without any problem. So then our number line is going to look like this. We've got 0, 10. We've got an open circle because there's no line underneath here, right? It's not going to be, a 10 is not a solution because 10 is not less than 10. And we're going to draw an arrow to the left. I'll scoot this on up and we'll go to number 7. So in number 7, we've got 2x plus 3 is greater than negative 9. This setup is basically exactly like number 5. So if you look at the structure of how we're solving this out, we are going to be taking essentially the same steps that we did on number 5 for number 7. Right, we've got a linear term and a constant term and a constant term. So this setup is basically the same. We'll start by subtracting 3 from either side. Sorry about the bells, y'all. And so that gives us 2x is greater than negative 12. I'll then divide both sides by 2. And that gives me x is greater than negative 6. I kind of forgot to mention this in the last one, but when you do this division, you definitely want to just do a double take and make sure you're not dividing by a negative where you have to flip the sign. In this case, we're not. We're dividing by a positive, so we don't have to do anything special. But you do want to just, like I said, take a double take, just take a step back, like, wait a minute, do I need to flip the sign? And just kind of ask yourself that every time you're working this problem out towards the end. Our number line graph for this would have 0. 6 is negative here, so it's going to be on the left of that of 0. And we'll put an open circle at negative 6 with an arrow going to the right. Number 8 is set up kind of like number 6, where we've got our constant, our lone constant on the left-hand side. So we can kind of expect that we're going to have to do something like what we did up here, where we just flip the whole fraction, the whole inequality to get it so that x value is on the left side. But we can wait till the very end to do that. First, we'll subtract 6 from both sides. And that gives me 14 less than or equal to negative 4x. Here I'm dividing by negative 4, and this step where I'm dividing both sides, this is where I do that double take, that little second check, and make sure that I either am or I'm not dividing by a negative. Now in this case, clearly I'm dividing by a negative number. So that means I have to flip the sign, flip the inequality sign. That means that this less than or equal to is going to become a greater than or equal to. Now, 14 divided by negative 4, I think that'll come out to be a terminating decimal. So we could probably write this one as a decimal, but you could also write it as a fraction. This will reduce fractions for you if you know how to do that. So you hit alpha, y equals to set up this little fraction. And if I do 14 over negative 4, not 3, negative 4, notice it'll automatically do the reduction for you. So you don't really need to worry about how to reduce here as long as you know how to get the calculator to do it for you. So this would be a correct number to put there. But if I do negative 6 divided by 2, I do get a terminating decimal. So this one's kind of up to you whether or not you want to do the decimal or the fraction. If you end up with a fraction like, let's say, 7/3, where you get this non-terminating decimal, you don't want to write this as a decimal. You want to leave it as a fraction. So as just a general rule of thumb, fractions are usually better than decimals. But if you can write it as a terminating decimal, you're free to do that. If I want to write this as negative 3.5 is less than or greater than or equal to x, that's fine. Additionally, if you'd rather write this as negative 7/2, that'll work too. Okay, either one of those is okay. You just want to be careful if you've got something like 3/7 or one of these fractions that turns out to be this long decimal. I don't want you to round or anything like that because then you're changing the value of the number. Instead, you just want to leave it as a fraction. Don't bother trying to write that as a decimal. A good rule of thumb is like if there's less writing for the fraction, go for the fraction. Okay. If there's less writing to write it as a decimal, then go for the decimal. All right. So anyway, I want to try to get that x on the left-hand side, mostly just so it looks a little nicer. It looks more like how we typically write these inequalities, but also so that we can take advantage of that little arrow trick. That's always nice to have. So I get x is less than or equal to negative 7/2. That is my solution set written as an inequality. If I want to give a visual representation of that solution set, remember, this is negative 3.5. And your scaling here is not really that important as long as it's like on the correct side of 0. That's what's really important there. But anyway, you have a closed circle and an arrow going to the left. All right, well, that's section 2. So let's jump over to section 3, which is really more of this stuff. Okay, there's not really anything different. The only thing that's different in section 3 is that there's just more stuff going on. Okay, so these are more like the harder equations that we saw in Unit 1. Where you've got to deal with the distributive property and combining like terms and all that kind of good stuff. So 9 says negative 4 times 3 minus 5x is greater than or equal to negative 6x plus 9. So whenever you have a situation where you've got like some number times either either a sum or a difference, like something plus something or something minus something. This plus or minus, I'm just saying it could be plus or it could be minus. But the way you handle this distributive property is you multiply this number on the outside by every single term on the inside. So this would be like a times b, and then depending if it's plus or minus, that just stays whatever it is, unless one of these is negative, and then it'll reverse it. But plus or minus a times c. So this is called the distributive property. That's going to come up on our vocabulary assessment coming later. So you just want to be familiar with that name, distributive property. But we'll go ahead and utilize the distributive property here. I'm going to distribute the negative 4 by multiplying it both by 3 to get negative 12 and by negative 5x to get positive 20x. So from here, we've got both a linear term and a constant term on both sides of the inequality. So you have basically two choices of what to do next. And it doesn't matter what order you do these in because they don't really affect each other. So, but overall, what you're looking to do is get these linear terms with x over to the left and get these constant terms, the ones that don't have an x, over to the right. So you just kind of do whatever you need to do to get that to happen. And what I like to do is move the linear terms first and then the constants, but you're welcome to move the constants first and then the linears. These two steps are interchangeable. So I'm going to go ahead and start moving my linear term over to the left-hand side. So I have negative 12 plus 26x is greater than or equal to 9. And now I'm going to deal with the constants. So that means I'm going to add 12 to both sides to get to move this term over to the right-hand side. So I get 26x is greater than or equal to 21. I can tell right away this is not going to divide out evenly. These aren't factors of each other. So, one's not a factor of the other one. So that's fine. We'll just end up with a fraction here. We'll divide both sides by 26. And if it's a nice decimal, we can write it as a decimal. But let's check and see what the deal is here. So if I do, what was that, 21 over 26. Okay, so this is not a very good decimal, right? And what I mean by that is it doesn't appear to be terminating. There is probably some pattern in here somewhere, but I definitely can't see it. It might be more digits than this will display. So I'm just going to leave it as a fraction. I do want to do a quick check and make sure I can't reduce it. It's always a good practice to write your fractions as reduced fractions. So I'm just going to do a quick 59. Oh, goodness. 26. All right, there we go. And so it's already reduced. If that doesn't change, then there's nothing to reduce there. So the best answer here is going to be x is greater than or equal to 21 over 26, which, as we saw in the calculator, is about 0.8. Okay, so if we're looking at a number line, that's where we can expect to see it. The way I've been showing you these number lines have been all, in terms of, in reference to 0. So as long as you have it on that right-hand side, you should be good. Got a closed circle, and it's pointing to the right. So this is my solution set written as an inequality, and this is the solution set shown on a graph. Let's take a look at the next one. Number 10. Negative 2 times 5 minus 4x is less than 6x minus 4. So I'm going to start by doing the distributive property just like I did in number 9. And you'll notice I kind of want you to just be kind of glancing back at this problem just so that you can really see that what we're doing and the order of the steps and the structure of the solving process is the same on these two problems. You solve them essentially the same way. Obviously, the numbers are different, but in terms of what step you take when, that doesn't really change. So when I distribute that, I get negative 10 plus 8x is less than 6x minus 4. At this point, I'm going to try to get my linear terms, meaning the ones with x's, over to the left side, and then follow that up by getting the constants over to the right side. Just like I was talking about on number 9, the order of those two steps is not important because they don't affect each other. Just as, I just like to do the same thing every time on these, so I just get in a habit of moving all the linear terms first. That's just sort of personal preference, but it doesn't really matter in terms of getting the right answer or not. So at this point, I'm going to start collecting all of my constants over to the right-hand side. So I need to move this negative 10 by adding 10 to both sides. So notice this, if you're just like at a quick glance looking at these two problems, you can see how they look very similar in terms of how they're solved. And that's because they are. They're very similar in how you solve them. Okay, so let's finish this off. We want to divide both sides by 2. And so I should get x is less than 3. Okay, the number line graph here, no big surprises. We've done a bunch of these so far, so hopefully you're starting to pick this up. We want an open circle because it's not equal to, and the arrow is pointing to the left. All right, let's do number 11. We have 2x minus 3 is greater than 11 minus 5x. This inequality is sort of, it's one step ahead of these. In other words, like there's no distributive property. We're already at the point where we've got just a linear and a constant on both sides. So we're going to sort of pick up in terms of the process, like right here, okay? So like we're going to group our x's, group our constant terms, and go from there. So let's go ahead and move all of our linear terms to the left side. I'm going to add 5x to both sides. And I get 7x minus 3 is greater than 11. Then I will add 3 to both sides. That gives me 7x is greater than 14. So no big surprises here. Nothing really out of the ordinary or different than any of these other problems that we're solving. I'm going to divide both sides by 7. And we get x is greater than 2. So there's our solution set written as an inequality. If you write it using a number line graph, you'll have 0, you'll have 2, you'll have an open circle on 2, and it should be pointing to the right. So nothing really special happening with number 11. It's not a lot for me to expand on there because it's so similar to the other problems we already talked about. Number 12 has got one little thing that's different. Number 12 is a little bit more like number 9 and 10 because we have to deal with the distributive property. But what you'll notice is that this application of the distributive property, I don't even know if you'd really call it the distributive property rather than just calling it multiplication, because there's only one term in this set of parentheses. So just be careful there. You're only distributing the -3 to this one term. Versus where typically you would have 2 terms to distribute it to. And that's just because there's only one term in the parentheses. So when that happens, it's really just a fancy way of multiplying. You're not really applying the distributive property, you're just multiplying. But you can still sort of showcase it in the same way because at the end of the day, distributive property is just multiplication. It's just how you multiply a single term by a polynomial. All right, so we get 8x minus 6 is greater than or equal to, so when I multiply this out, I get -9x plus 5x. And here's something else that's a little different. We haven't seen this on any of the other problems yet, where we have 2 linear terms, and this would be the same if you had 2 constants on the same side as well, but they're on the same side. So what I want to avoid doing here is, like, for instance, adding 9x to both sides, like adding 9x, and trying to combine it that way. But what I do want to do is, if they're on the same side, you want to just combine like terms like 2 plus 3 is 5, that sort of thing. So in this case, we have -9 plus 5, which would be -4. So I'm going to do that step first before I start moving things around. So that would give me 8x minus 6 is greater than or equal to -4x. So now I can start to move things around. It's a little weird because, if I try to move this over here, I'm going to end up with 0, but that's fine. Don't let that throw you off. There's sort of an implied plus 0 here. If it helps, you can throw that in there. You don't need to, but, just know that if I get rid of everything on this side, there's still a 0 there. -4 plus 4 is 0. So we'll write that on the next step when we get there. Here I'm going to add 4x to both sides. And so this is right here is what I'm talking about. We get 12x minus 6 is greater than or equal to 0. So you're still left with a constant here, even though it's just implied up here. It's not explicitly written. 12x minus 6 is greater than or equal to 0. What we need to do is add 6 to both sides. And that gives us 12x is, let me move this up a little bit, greater than or equal to 6. And we want to combine, we're going to divide here, but don't be so quick on the draw to divide this, because what I see a lot is like you just say, oh, 6 divided by 12, that's 2. 6 goes into 12 2 times. But be careful here, because it's 6 divided by 12, not 12 divided by 6. So if there's any question at all, as far as what this should be, do it in the calculator. It doesn't hurt. 6 divided by 12, I just want to double check. I'm pretty sure I know what it is, but I'm just going to check. Okay, it's 1/2. That's kind of what I thought. 1/2 can be written as a decimal 0.5, and that is a short, terminating decimal. So if you want to write it like this, that's fine. If you want to write it like this, that's just fine too. I will typically stick with the fractions just because I like fractions. I think they're more efficient than writing decimals most of the time. Not all the time, but most of the time. Here's my solution set. So on my number line graph, I'm going to have 0. I'm going to have 1/2. I'm going to have a closed circle and an arrow pointing to the right. So that's the end of section 3. Section 4 is all about compound inequalities. So before I start going through these problems, what I want to do is kind of summarize what you need to know about compound inequalities. So compound inequalities are inequalities that have more than one statement. So like, for instance, instead of saying x is less than 5, you might say, oh, x is less than 5. Oh, but it's also bigger than 0. And so when a compound inequality has 2 separate statements, and depending on what kind of compound inequality you have, you either need to satisfy both of them or you just need to satisfy one. And I'll give you some examples of that to kind of make sense of it. So the 2 types of compound inequalities are or compound inequalities. You might have and compound inequalities. So for an or compound inequalities, compound inequality, you only need to satisfy one of the statements. In order to be a solution. So in other words, if I say x is less than 5 or x is greater than 10, you could pick a number like 3, and that would be a solution. Even though it's not greater than 10, it is less than 5. So that would be considered a solution. I'm satisfying one of the conditions. Like, let me give you an example of just like a true-false statement here, using these logical operators of or and. So I'm a math teacher. We'll just establish that. And we'll establish that I own a Nintendo Switch at home. So we'll just say that's true. So if I say I am a history teacher or I own a Nintendo Switch, you would say overall that statement is true because one of the statements has been satisfied. Okay, even though I'm not really a history teacher, what I'm saying is I'm a history teacher or I own a Nintendo Switch. So now if neither one are true, if I say, oh, I'm a history teacher and I own an Xbox, let's assume I don't own an Xbox. I don't. If I say that and then neither one are true, then the whole thing would be false, right? Because you're not satisfying either one. Now you're free to satisfy both. If I say, hey, I'm a math teacher or I own a Nintendo Switch, you would say, yeah, that's true because one of them was satisfied. In fact, both of them were. But if one of them is false, so if I say I'm a math teacher or I own an Xbox, since I don't own an Xbox, you might be tempted to say, oh, that's false. But since I'm using the or operator, I only need to satisfy one of them. So if I say I'm a math teacher or I own an Xbox, it's still a true statement overall. So here's a little pro tip for you. If your parents ever ask you, hey, did you clean your room tonight or did you leave it messy? You can say yes, because one of those things has to be true. Okay, you don't have to pick one and say, I did this or I did this. You can say, yes, I did leave my room messy or clean it up. One of those things is true. Now, they might not like that. They might call you a smart aleck or something, but it is a technically true statement. And in math, we don't really care about anything except for when it's technically true. Okay, so Anyway, that's the deal with the or inequality. When you see or inequalities, typically they're going to be written with the word or. So you're going to see something like x is less than 3 or x is greater than 10. Now, obviously, there's not a number that would satisfy both of these, right? Like if it's less than 3, it has to be smaller than 10. So there's not a number that's both bigger than 10 but smaller than 3. So if this was an and inequality, there'd be no solution here. But since it's or, we only have to satisfy one of them. So all the numbers less than 3 are solutions. All the numbers greater than 10 are solutions. The way you would see that on a number line graph would be if let's throw in 0 and a 3 and a 10, is you would have, you'd have open circles for both of these, and the arrows will be pointing in either direction. Now, this isn't true for every or statement that exists, but for all the ones that we are going to be dealing with for right now, the graph is basically going to look like this for any kind of or compound inequality, meaning like the arrows are going to be pointing outward. There are some cases where, some sort of corner cases where your graph looks a little bit different than that. But for the most part, you can expect that the graphs are going to look like this with the arrows pointing in either direction for an or inequality anyway. Okay, so that's what what you need to know for or inequalities. For and inequalities, now this is different in that you don't just need to satisfy one of the statements, you must satisfy both statements. Okay, in other words, if I say I'm a history teacher and I own a Nintendo Switch, that would be false, because even though I do own a Switch, I'm not a history teacher. And when I'm using the and logical operator, I've got to satisfy both. So I would have to say something like I'm a math teacher and I own a Nintendo Switch in order for it to be true. There's two ways we can write these and inequalities. You might see them occasionally written sort of like with this formatting where you actually write the word and, something like x is less than 10 and x is greater than 6. But usually you won't see it written like this. There's a sort of a shorter, more efficient way of writing and inequalities. And that is if x is basically in between two numbers, so like bigger than 6 and less than 10, you can write it like this, where x is in between 6 and 10. Both of these are logically equivalent, but as you can see, this is a little bit more efficient way to write it. And for the most part, you'll see your and inequalities written like this. So if you see a number in between, or an x value in between two numbers, that's your clue that, hey, this is an and inequality. With these and inequality number line graphs, the way that they'll work, for the most part, again, there's always like exceptions to the rule, but for the most part, what we're going to be working with is you're going to have your circles and you're going to pay attention to see if they're closed or open, and these two are open, just kind of like, all right, you know what, just to kind of make this a little bit different, let's say that these are going to be equal to, just so we can throw in some closed circles on there. And they might be different, like one might be open, one might be closed. That doesn't really make a difference. You don't need to worry about that. It's just you make sure that your dot matches up with the sign either way. And then since x is in between these values, you just connect the dots. Okay, so if you ever see something like this for right now, it's mostly safe to assume that's going to be an and inequality, a compound inequality. So this is sort of the short and sweet of what you need to know about like what compound inequalities are. So let's look at the problems on the review now. 13 and 14, you're just writing the inequalities. So number 13 says, in order to avoid heavy traffic, Antonio can drive home after working less than 7 hours, or, so right away, it's an or statement. Just gonna like throw that out there. Or working more than 9 hours. How can this be written as a single compound inequality? So what we would do is say x could be less than 7, or x could be greater than 9, where x represents the number of hours that he's working. Okay, so you're really just kind of rewriting what it's saying in English as an algebraic statement. That's pretty much it for that one. Number 14 is a little trickier because the endpoints are not as explicitly stated. Okay, so what I'm going to do with, you know what? Let me do this as a number line first. It doesn't really ask you to do it as a number line, but it's good practice just to kind of get in the habit so that you're familiar with them. So this number line graph would look like this. So number 14 says in order to be invited to tutoring or extension activities, a student's performance must be at least 20 points higher or lower than the average score. If the average score is 105, write an inequality that represents the scores for students who are eligible for tutoring or extension activities. So basically it's saying that, hey, if you did really poorly, you're going to be eligible for tutoring. If you did really well, you're eligible for these extension activities. That's sort of an implied piece to this, just so you understand the context and can better interpret what your answer represents. But anyway, so in order to be eligible for the tutoring or the extension activities, you've got to be at least, meaning it could be 20 points or it could be more or less. It could be like 40 points, either above or below the average. So this one's a little trickier because it doesn't explicitly tell you what these endpoints are. We have to kind of figure them out. So what I'm going to do is actually, I'm going to work this kind of backwards and start with the number line graph to help me kind of piece this together. So it says the average score is 105. So I'll throw 105 here. And then it says your student's performance must be at least 20 points higher or lower. So I'm going to go 20 points higher and 20 points lower and label those are the numbers that we're working with here that will have the dots. So 20 points higher will be 125. 20 points lower will be 85, right? So if you get less than 85 points, you are, you're good. You're eligible for these tutoring services. And if you get more, oh, it says at least, so it could include that too. So let's do a closed dot on there, because that's when you see the word at least, that means that endpoint is going to be included. And it could be greater than 125. So the way I would write this would be x is less than or equal to 85, or x is greater than or equal to 125. I didn't box those earlier. By the way, the variable I'm using here, x, not a big deal. That can be whatever you want. It's not specified in the problem what letter to use, so you're kind of free to do whatever you want. All right, number 15, write a situation that could be represented by the graph. So this one, you've got a closed dot on 8 and an open dot on 11, and then the number line is in between those. So the way that would look as an inequality would be something like 8 is less than or equal to x is less than 11. Notice the closed circle and the open circle. You could also write it using the word and if you really want to. X is greater than or equal to 8 and x is less than 11. But I really prefer this one, and I think most people would. It's just a more efficient way to write it, and I feel like it's clearer. And it can help you understand what's going on a little bit better. So it also asks for you to come up with some situation that would be represented by this. That could be anything. You'd be like, over the next 2 weeks, I want to make sure to work at least 8 days, but not more than 11. Or I think the one in the key said, to make the perfect biscuits, you must use no less than 8 cups of flour, but fewer than 11 cups. So the situation or the context, that's up to you. There's not like a single right answer. As long as this is sort of the inequality you're working with, you'll be okay. Number 16 is another and inequality. It would be 12 is less than or equal to x is less than 18. So you could write a similar statement here that you did for 11, just switch out the numbers. Basically, any situation where you're between 12 and 18, including 12 but not 18, you'll be safe. And this is another and inequality, so you might see it written like this. Not likely, for all the reasons I've stated before. This is really going to be the one you want, but this is not wrong either. Number 17, it's just asking us to graph the compound inequalities. So if I have -3 less than x less than or equal to 6, I'm going to have my 0, my -3, and my 6. Here, x is in between these two. This is strictly less than, so I'll have an open circle. This is less than or equal to, so I'll have a closed circle. And this is an and inequality. X is in between these, so my solutions are going to be in between those two values. And finally, to cap this off, we've got x is less than or equal to 4, or x is greater than 14. So in other words, we only need to satisfy one of these to be a solution. So all the numbers that are less than or equal to 4 will be solutions, and all the numbers that are greater than 14 will be solutions. The way that looks on a number line graph, I'm going to throw 0 on there as my reference. 4, 14. I've got a closed circle at 4, and the arrow is going to be going to the left. I've got an open circle at 14, and the arrow is going to the right. And that's it. So I think definitely this compound inequality piece is probably the hardest part here. The rest of this solving stuff, honestly, is the same that you did in the last unit. Really, the only thing you got to look out for is this whole dividing by a negative, which didn't on this review happen that often. In fact, it looks like it only happened like 1 or 2 times. You know, we saw it over here, dividing by a negative, got to flip the sign. We saw it in the very beginning, but there wasn't a whole lot. And that'll probably, you could probably expect that on the test where it's not going to be every single problem where you got to worry about flipping the sign, but it is going to come up here and there. So you want to be double checking that every single time. So that's pretty much it. Let me know if you got any questions about any of these problems, and I'll be sure to help you. Other than that, good luck studying, and I'll see you around.